semantically correct, but can have different representation compared with IR generated by the compiler. For example, variables in C code will be translated into corresponding variables in clone-generated IR. But in Maxima-generated IR, variables will be represented as members of two special structs named state and mem. Also, the function prototypes will not be recovered in Maxima-generated IR. As shown in Figure C, functions in Maxima-generated IR always have two arguments, status and mem, which represent hardware state and the memory objects separately. As we observed that the lifted IR code can have visually different representations with IR produced by compiler. The different representations could likely hinder downstream analysis. So we wanted to ask, to what extent the lifted IR can support representative downstream applications? However, expressiveness is hard to define formally, and therefore we measure it from an empirical perspective. More specifically, we want to demystify the expressiveness of binary lifters through the lens of representative downstream applications. We use downstream applications including discriminability analysis, pointer analysis, CT compilation, and address sanitization. Overall, in this work, we conduct an in-depth study of binary lifters. We study 4 popular lifters developed by academia and the industry with downstream applications including neural code comprehension, static value site analysis, RedDeck CT compiler, and the clone address sanitization. Yeah, we conduct such a study in a cross compiler and a cross-platform setting. Now let me briefly introduce the downstream applications. Pointer analysis establishes which pointer can point to the same variables or memory objects. It is the cornerstone of most data and control flow analysis. We leverage the state-of-the-art LLVM pointer analysis library, SVF. Discriminability analysis determines the similarity of 2 pieces of IR code that implement the same or different task. It is the base of various similarity-based security applications. For instance, malware clustering and code plagiarism detection. We reuse the code embedding tool, NCC, published in NIPS 2018, which converts similar IR code into numerical vectors with close distance. CD compiler conducts a set of analysis passes to the IR code and converts IR code into high-level C source code. For this task, we use the decompiler component provided by the RedDeck framework, which is the best available LLVM IR-based C decompiler according to our empirical observation. And the AddressSanitizer is a well-known memory exploitation protection mechanism. In this study, we use AddressSanitizer provided by Clone. We benchmark 4 lifters, including Maxima, developed by 12-bits, Macto, developed by Microsoft, RedDeck Bin2 LLVM, developed by Avast, and BinRec, published in Eurosys 2020. To review how compiler optimizations could affect the performance of downstream applications, we configure Maxima to disable all imposed optimization passes as maximum 0. Overall, we think that compiler-generated IR denotes the upper bound quality of lifted IR. We empirically benchmark how far we are from the perspective of the downstream applications. Instead of defining how good the lifted IR should be with regard to downstream tasks, we check whether lifted and compiled IR has comparable performance. Then here are the findings of this study. One of our major findings is that currently existing lifters follow two distinct patterns when producing IR code. We distinguish them as emulation-style IR, abbreviated as EIR, and high-level IR, abbreviated as HIR in the following. Generally, EIR is functional and executable, as it tries to emulate each hardware instruction faithfully with IR code. However, such IR does not contain valuable information, including variables and types and even function prototypes. On the other hand, HIR is concise and easy to understand but usually not functional, as accurately recovering variables and types from stripped binary is challenging. Here is an example. As shown in this figure, a simple move instruction in assembly code will correspond to a sequence of load and store instructions in the EIR code. But HIR code lifters will analyze this code snippet and summarize the two move instructions as an argument of a function call, which is close to compiler-generated IR. Basically, EIR represents CPU registers with global variables and use multiple IR instructions to achieve the semantics of an assembly instruction. And thus, EIR is usually more lengthy and difficult to be understood by analysts. We find that all lifters have trivial support for pointer analysis. The main reason is that pointer analysis relies on accurately recovered variables and types. However, 100% recovering is challenging and undecidable in reverse engineering. Besides, we find that lifters failed because of two different reasons. BinRAC and Maxima, which produce EIR, failed because EIR naturally does not support pointer analysis, as function prototypes and variables are not recovered at all. And for RedDeck and Mac2, which produce HIR, they failed because variables and types are not correctly recovered. We further investigated their algorithms and found that lifters have not fully implemented research products in the reverse engineering field. Nevertheless, RedDeck can leverage debug information to refine its output. Thus, we are able to enhance pointer analysis results with the help of advanced methods in reverse engineering. For example, dbin, which published in CCS 18, can be used to predict the debug information for stripped binaries. For discriminability analysis, we find that HIR generally outperforms EIR, and optimization can significantly improve classification accuracy. Also, IR lifted by HIR lifters, like RedDeck and Mac2, has comparable performance with even compiled IR. For decompilation, we follow existing research and measure the structuredness of decompiled C code by counting the go-to statements and the average line of code. We find that compiled IR generally exhibits better performance than lifted IR, while IR lifted by RedTech has a close performance with compiled IR. Besides, we also recompiled all lifted IR to check their functionality correctness. Most IR lifted by EIR lifters, such as Maxima and Binrack, can pass the test cases, while HR lifted by RedTech and Macto show lower success rates. This result again demonstrates that modern binary lifters have distinct designs. EIR lifters focus more on functionality, and HR lifters focus more on readability. We also compare retrowrite, an advanced binary rewriter, with binary lifters in applying AddressSanitizer to executables. We find that Maxima has appealing utility. Although stack variables are not recovered in lifted IR, Maxima shows heap sanitization performance comparable to retrowrite. Overall, we summarize our main results in this table. Note that RedTech can be enhanced with debug information predicted by dbin. Thus, pointer analysis accuracy of RedTech can be improved. We denote this in the second row with an extra arrow. Finally, we concluded this study with several takeaway messages. First, LLVM IR optimization plays a critical role in generating concise and discriminable IR code. Second, state-of-the-art lifters cannot recover variables and types accurately, but some advanced research output can be used to enhance the performance. And third, binary lifters have distinct preferences. EIR lifters focus on functionality, while HIR lifters focus on readability. Also, HIR lifters can produce IR code that has comparable performance with even compiled IR on the discriminability analysis task. That's all of the presentation. Thank you for listening, and I'm glad to take some questions.
All right, do we have Zhibo on Zoom to answer questions?
Yeah, I'm here.
All right, any questions? Please come up to the mic so he can hear you. Otherwise, I'm going to start with a question. So I'm wondering, so generally the performance didn't seem that great, for instance, on the decompilation task. But if you think about tools such as Ghidra, which do use an IR, their own one, P-code, and do have reasonable decompilation performance, is it maybe the case that LLVM is just not a very good IR for reversing tasks? Like, should we use a different IR?
Yes, we actually compared the decompilation code generated with LLVM code with the output of the Ghidra and AdaPro. We found that actually the commercial tools AdaPro and Ghidra can outperform current decompilation results based on LLVM IR. But we also found that if we use clone-generated IR, then use the RedTech decompiler to decompile the clone-generated IR, we will even get better results compared with Ghidra output and AdaPro's output. So in this view, we think that maybe currently the lifted IR doesn't show very good results on decompilation task. But in future, if we can continue to improve the quality and the functionality of the lifted IR, maybe finally we can get a better LLVM IR-based decompiler compared with some expensive commercial tool.
Ghidra is not that expensive, but okay, thank you.
Yes, Ghidra is free.
We have a question from the audience.
Yes, so thank you for your very interesting talk. I'm Kyle Zhang from Arizona State University. So I have a question about the data set that you have, which is 4 or 5 binary lifters. Not all of them, actually many of them are not designed for reassembly analysis. But there is actually one more binary lifter that can lift binary into a VMIR that is specifically designed for reassembly, which is called RevNG. So I'm wondering why RevNG is not in your data set, and because it's kind of famous. And did you try it? Was there any issue with it?
Yeah, we actually investigated RevNG, but actually this work starts from 2020 summer. So at that time, we investigated RevNG, and we found at that time the documentation is not very detailed. So we tried some toy example and didn't figure out a way to use RevNG to generate functional IR. So at that time, we decided to not include RevNG in our evaluation set. But we recently investigated the RevNG, and we found that this tool has a continuous development, and it's continued to be improved in last 2 years. And we found this tool can actually generate some high quality functional IR. So we think this work is conducted in mainly in last year. So we think the results present in this paper may not fully reflect the current state of modern boundary lifters. So we think if users want to choose a lifter for some specific tasks, they maybe should turn to the current maybe developed version or latest released version of the boundary lifters to get better results than presented in this paper.
I see. So it will be interesting to see the latest evaluation. But thank you.
All right,
Yes,
thank you.
Thank you.
Let's thank the speaker again.